Hello everyone. So if you're following me along, you have seen that we have covered the foundation arc in the beginning in the first 6 sessions. You have seen how to work with the LLMs, how to build a basic AI agent and or even an intermediate level of agent reliable up to certain extent without using any framework. Thereafter, you have seen we have moved toward OpenAI SDK. We have created an agent with concepts like runner and function tools, and we have seen how they have made creation of agents so much simpler. And then we have built the multi-agent system using concepts like handoffs. And we have not stopped even then. We have introduced more reliability into the agent's behavior using concepts like guardrails and tripwire. But from this session, we are changing the direction. And so instead of answering question when the agent should act, which agent should act, we will be answering questions like what the agent should know and how to produce quality output with the help of LLM. And this shift brings us to the one of the most important concept in AI engineering called RAG, retrieval augmentation generation, a concept so critical that we have devoted next 6 to 7 sessions to cover all the important concepts or trade-offs or frameworks related to that. So without delay, let's get started. So what is RAG, which is retrieval augmentation generation, is all about? Before going into the details, let us first try to understand the problem it is trying to resolve. So the problem is LLM does not know everything. Yes, you heard it correct. After its knowledge cutoff date, any new information is invisible to the LLMs. And the same is true about the company's private information, the internal documents, database, PDFs. None of it was the part of its training set. So what does the LLM does in such scenario? It hallucinates. It does not always say no. It fills the gap with the confident, plausible sounding guess. So what is the solution? Won't it be good that if we provide the LLM with the relevant context, the right information when the user is asking the query, so that instead of referring to its training data, it refers to the contextual information provided to it. So how can we do that? There are two ways. Let's understand this with the help of an example. See the below of this workspace. Suppose say that company A is developing a chatbot, AI-based chatbot for its internal employees to ask any question about company's internal policies. And the company also has a huge set of internal documents or PDFs in which these policies are stored. So the one way to go forward is and LLM returns the response grounded in your data instead of using its training data. So this is without RAG, directly providing all the relevant documents to the LLM. So think about it. Is this the right way to do it? I mean, the question is this even possible? So the answer is technically or theoretically it is possible considering the long context right nowadays provided by popular LLMs. So what is context window? In case you are not aware, it is total token LLM can process in one interaction. It includes both input as well as output. And token, if you don't know, is a unit of text that can represent a word, part of the word, or even punctuation marks and spaces. Roughly 100 token is equal to 75 words. So models, if you can see below, they can have context window of 1 to 2 millions of tokens. And if you see here, the Grok supports up to 2 million tokens, which is roughly equal to 1.5 million words. To give you further context, you can practically feed all the Harry Potter series books, which cumulates to 1.5 million words across its 7 books as a part of user query. So in other words, the context window can be large, but is it possible or is it viable and feasible to provide all such documents every time the user asks the question? The answer is no. Why? Because it leads to so many other problems. The first is the noise problem. If you see here, the large context window means you will be providing not only the relevant data, but also a lot of irrelevant and repeated data. So model will run into needle into haystack problem. It has to sift through large amount of data to give you the right information. And moreover, like it will have, embedding dilution issue. Performance definitely when it has to go through so much amount of data in order to find the right answer, then it means it will be slow and definitely the cost impact. So if you are aware about in LLM world, more tokens means higher cost. So what is the solution? Think about that. Won't it be good instead of providing all the documents, all the company policy at the time of user query, instead of that, if we can just provide the relevant chunks of right info from the right documents, so that the window remains small and LLMs can process them quickly to find the right answer. So this is what RAG is all about. R means retrieving the relevant checks of right info from the right documents. A is augmenting your user query with the relevant checks obtained during the retrieval step. And G finally means generating the grounded response with the help of LLM. Now augmenting and generation sounds quite usual, and they are. So the key engineering challenge of the technology of RAG is something which happens during the retrieval step. So for that, what we have to do, we have to divide our documents into the chunks, which are converted into something called embeddings. Embeddings and vectors are used interchangeably, but there's a meaningful difference between them. And they are finally, these embeddings are stored in something called vector database. So to understand it in little bit more details, we have to understand what vectors are. So vector, as you see from this screen, it is just a list of number. Each number represents one property of something. Suppose a book can also be described as a list of four numbers: genre, pages, years, and rating. So as you see here, these are the two books I have defined with one of type fiction. The first book has a number of pages 200, year of publication 212, and 4.5 ratings. The other book also looks relatively similar, but the next book looks quite different because it is non-fiction, number of pages are different, year of publication, there is a vast difference, and the ratings also looks different. So the key insight here is numerical closeness has some meaning. Two vectors that are close represent two things that are similar. So in RAG, what we do, we convert our text into such high dimensional vectors, but they are not just four numbers, they are hundreds or thousands. As you see here, if you use OpenAI text embedding model, so it produces vector in 536, sorry, in 1536 dimensions. Another concept to note here is in embeddings, direction is something which encodes meaning. So the two vectors, if they are pointing to the same direction, that means they are related to the same topic, regardless of their length. So now let's see just this document. And here again, we have defined the vector. Vector is just a list of number. In two-dimensional space, you can represent the vector like this. In RAG, what we do, we convert the text into high-dimensional vectors. We have seen like it can be 1536 dimensions. Instead of four, we can have hundreds or thousands of numbers. Now come to the key point. What is the difference between vector and embedding? So vector is just a data structure, array of number, list of number. It has no meaning by itself, but embedding means it is a meaningful representation. It is the list of numbers which are created by trained model. It captures semantic meaning. So image, text, video, all can be stored as embedding. So the key difference here is embeddings are not equal to vectors. Embeddings use vectors to represent something. Another concept is metadata. It is the data that is stored along with your embeddings. So as you will see later, once we convert the text into embeddings, when we store the data into the vector database, we also store the metadata. What is that metadata? It can be, section title, paragraph, publication data, any other information, because this is information that is helpful in optimizing the performance of your RAG application. We will see this concept in one of the later sessions. So now the question comes how you measure the similarity between the vectors. There are three things involved here. One is Euclidean distance, cosine similarity, and dot matrix. So Euclidean distance measures the physical distance between the vectors. As you see here from this diagram, if A and B are two vectors, so Euclidean distance measure, which is also called L2 distance, it measures the distance between these two vectors. Cosine similarity measures the angle. And the dot product, it is something which measures both the direction as well as the magnitude. So summary here is all measures closeness in a different way, and cosine similarity is preferred in the RAG application because meaning of text is captured in the direction. So the length of vector is generally not that significant when we have to create a RAG based application. Now how to convert vector into the embeddings? So for that we have to use embedding models. The first one is OpenAI embedding models. We will go through it. We will do an example here. But the key point here is it runs on OpenAI servers. It requires an API call. It produces vectors of very high quality, but the trade-off is there's some cost, because definitely there's some cost involved while making the call to OpenAI server, and some latency because we are making the API call. So another way to convert text into embedding is using the sentence transfer Python library, which provides embedding capability via open source model available via Hugging Face ecosystem. So if you don't know the Hugging Face, it is kind of AI platform for pre-trained models and datasets. You can see there are some trending models here. Similarly, there are datasets which are available. So it is kind of GitHub for the LLM models. The point to note here is models, once they are downloaded, they run locally. So the first time they will take some time, but after that they are very fast. No API is needed after the download. Another point to remember is you have to use the correct model depending on the type of data. So the text embedding models cannot be used to embed the images. Or as you see here, there are clip model specific models which are available for image embeddings. Now, before proceeding further, let's do some coding to understand how we can convert text to embeddings. So for that, I have already created a one project, and I have already created the .env file, added my OpenAPI key, created a blank text file. Now let's add some code here to understand how the embedding works using the OpenAI embedding model. So as you see here, we have imported some packages from OpenAI. We have imported OpenAI class using the load underscore .env module. We have imported the .env functions. We are first loading our .env file and then instantiating our class as we have done previously multiple times. By this code, this is a simple line of code. You can very easily guess what it is doing. We are using our embedding model. We are passing the input and we are passing the model and we are generating the response. This is the way to get our vectors back. And we are just printing it. We are printing the length of the vector. We are printing the first 20 values of the list of the vectors which we are getting. So let's see how it works. So as you see here, if you can see, it is showing that the vector dimension 1536, something we have noted earlier in our presentation, and the first two values, because there are 1536 values, the first three, the first 20 values, it is showing it here. So this is how the embedding works with using the OpenAI embedding model. Now let's quickly see how the sentence transformer works. For that, we will create another Python file. So if you, as we have noted, it does not require Open API key. So the models once downloaded, it will run locally. So for that, you have to just install the sentence transformer Python library. Once this is done, you can just run this code. So if you see here, we are just importing the sentence using the sentence transformer module. We are just importing the sentence transformer class. We are instantiating it with the model name, and then we have our text and getting the vector back. In the background, there are certain, dependencies like PyTorch and all, but those are handled automatically. You don't need to worry about that. So let's run this class also and see how it works. So it took some time, but as you see, our program runs successfully. The short snippet we have added, and the vector dimension here case is quite less, 384 as comparison to 1536, and the first 20 values are printed. So I hope the concept of embedding is now clear to you. Let's move ahead. So another question which generally comes to people's mind is, what is the difference between RAG and fine tuning? In other words, why not just fine tune the data instead of using RAG? So the answer is, the fine tuning is quite expensive process. It needs GPU time and label data, and as well as it is quite static because the information is baked into the model weight. It does not update periodically. So think about, like, you have printed the book. Once it is printing is done, you cannot easily go and change the book unless you come out with the new edition, right? So returning is required when the data changes. Whereas in RAG, it is comparatively quite low cost. You update the vector database, not the model. Quite dynamic, works well with the latest data, and you can swap the document easily without touching the model. So in swapping, if you can think so, you have to first delete. Obviously, there are some steps involved. You have to delete the existing document, which is now stale, which is now old, and then you can do the chunking and add the new document. So there are some steps involved. The key step here is how to find the right document which you need to replace. And for that, the concept of metadata, which we have covered earlier, will play a key part. So when to fine tune, you want the module to behave differently, tone, format, style. When to use the rack, when you want the model to know something it doesn't. They are not competing approaches, they are complementary. So now all the basics already covered. I think it's the right time to finally go through its architecture and implementation or process. So it has two parts. One, first part has some pre-steps. So you have the raw data, you convert them into chunking, then into the embeddings, and finally those are stored into the vector database. We have seen the same through this diagram also. You're converting the text into the chunks, then into embeddings, and storing into the vector database. The second part is the key part, which happens at the time of user making the query. So when the user fires the query, you convert that into the embedding and you search the nearest vectors closest to the meaning of what user has asked for in the vector database. And then you retrieve some top relevant chunks as a part of retrieval step. And then finally send those details to LLM along with user query. We call this as augmentation, and finally generate the answer. The same you can see from this diagram. On the left side, we have data preparation steps. You are preparing the data, you are extracting the information, then you are chunking it, converting them into embedding, storing into the vector database. And then when user is supposed to asking the question through a chatbot, convert that into the embedding and search the nearest possible vector through vector database, retrieve the relevant chunks, pass to LLMs, and get the response. I think this process should be now clear to you because all the basics were already covered earlier on. One thing to just note is, when you will go through RAG, you will heard a name quite often, which is called retriever. So retriever is nothing but just a component, or you can say a function in Python, whose job is to embed the user query, perform the vector search, and return the result. So in other words, the three steps which are covered here, you convert into the embedding, the user query, search in the vector database, and retrieve the relevant chunks. You perform it with the help of retriever. An important concept to cover, because so now the RAG architecture clear. I think one other concept to be you should be clear about is chunking. I mean, the question should arise in our mind, in what proper ways the chunking is done so that the relevant data and relevant chunks are retrieved for the LLM consumption. So let's go to the chunking. And chunking is not the most easy step of the entire RAG architecture. So that's why learning about is important and as well as very much critical. So chunking, as we understand, is you split the large document into smaller pieces. It should be small enough to be consumable, coherent, as well as contextual. So it should not be very much large so that LLM is not able to consume. Not much relevant term in nowadays because LLM has very large context window as we have seen previously. And they should be coherent, easily understandable chunks and contextual related to the question which is asked by the user. Ideally, it should be single or set of complete thought instead of the part of the sentence. So like you see here, suppose you have a document of 50 pages, you can chunk it in multiple paras, embed, and store in the vector database. But there are different strategies, right? How you can convert the chunk into paras. Is there an easy way out? Because each para can have a different number of characters. So let's go through some of the details. As you see here, suppose say this is the text which we like to chunk. Now there is some strategy called fixed size strategy in which you divide the text into based on the fixed number of tokens as or characters. So, but if you will do it, abruptly cutting the text into different chunks. To overcome that, in order to prevent the loss of meaning at the boundaries, you do something, you also add something called chunk overlap. So, chunk overlap, you add the sum of the text of the previous chunk to the current chunk so that the meaning is not lost. But I think if you will see here, this is not the best way. Even you have add some extra characters or token here, it is still not giving the proper meaning to the chunk which we have got based on the fixed site chunking. So that is why there are various different chunking strategies. And another thing to in mind, chunking size should not be too small or too large, because if it is too small, then important surrounding information gets split, leading to the fragmented understanding. You will have definitely a high precision because you will get the chunk which is related to the question which is asked, but there will be incompleteness because the size is less. And definitely it will require more vector to store and such, and will add to the retrieval cost. It's better for the very specific question, but single chunk may not contain the full answer. And similarly, but if the chunk size is too large, then there's always a problem related to the context dilution. Multiple topics will get merged, weakening the semantic focus. And as you can guess it, it will have low precision because matches become fuzzy due to the mixed content. Number of vectors will be less, but it reduces the effectiveness of similarity search. It's used for the broader queries when the question spans across the multiple ideas, and retrieved chunks can include unnecessary information. So that is why, if you see here, neither we can keep the chunk too big, too small. There are so many problems if you cut the sentence in between. So that's why there are multiple chunking strategies which we are adopted. One we have seen above, fixed size strategy. Like as we have seen above, we slice the text into rigid token or character counts. Usually include a small buffer. We have seen like we can include the overlap buffer overlap to prevent losing the context at the seams. It is useful for the short form content like the internal mail, but it's not the best. You will see like people generally prefer recursive strategy even at the starting because it uses a logical hierarchy. So you first divide the text into paragraph. If paragraph is not possible, you divide it by sentence. If sentences is not possible, suppose if the sentence is very large, you divide it by the word. So it is generally used for the blog post or product documentation. Third is basically document based chunking, where you do the splitting based on the tags like headings, H1, H2, or HTML sections. So basically useful for technical manuals or where the structured markdown, where you can do such kind of division based on the tags or based on the header. So the next is the semantic. It uses the NLP to detect the shift in the meaning. Here also, to divide into the chunks, you use some kind of embedding model. So it cuts the code only when the subject changes. So you can guess it if suppose say two sentences are different in meanings, if their vector distance is large, then only you perform the chunking, otherwise not. So it is useful for the research papers or dense technical specs where losing the thread of the argument break the retrieval. The next is agentic one. Agentic, here you use the actual LLM to divide the document into chunks. Basically, it reads the text and determines the most logical boundaries. So it is useful for the legal contracts or regulatory filing where human-like understanding is required to break the document into the chunks. And the last is hierarchical chunking. Here we basically index the text at multiple levels. So parent-child relationship kind of text. As you can see here, the example is given below. So you have a global annual policy document. You have a section one, which has executive summary of all the different kind of leaves, and then the individual sections, which tells you the details of a particular kind of leave, like annual leave, sick leaves, maternity leaves, and all. So this is some kind of parent-child relationship. So that is why in the scenario, the hierarchical chunking is required. A bonus strategy is post chunking strategy where the chunking is delayed till the query time. So you don't chunk In the as a pre-processing step, you embed the entire document, but at the query time, you first find the relevant document and perform the chunking, and those chunks are basically sent to the LLM. So why it matters? Because it avoids unnecessary chunking of documents that are never queried, and it enables dynamic context-aware chunking based on the query and improve efficiency over time. So some chunking scenarios, if we will go through it, let's say this example, short intro. Suppose there is a one paragraph which is giving short intro of something, then there is a another paragraph, and then there's a very long paragraph. So can you tell me how you will do the chunking here? The answer is recursive chunking, because you can break into the first and second paragraph, and third paragraph, which is long, it can be, broken further by the sentences, right? So it is very adaptive. Chunking is adaptive using this approach. Let's say take one more example. There could be so many other example also, but just to give you idea, suppose say there question answer. So the answer is better you do it with the help of semantic chunking, because question and answer are linked with each other. You cannot divide it by paragraph or sentences or anything like that. You can use even the agentic chunking also, but it will be costly. So that is why wherever possible, you should prefer the semantic chunking over the agentic chunking. So I hope the basics of RAG and all the related terms like chunking, embeddings are all clear to you. In the next session, we will go through vector DBs and similarity search. We will go through find out what the similarity search is all about. We know now a little bit about it, but we will cover it in detail. We will also find out how why the traditional DBs are failing. We will cover the vector database, KNN and ANN algorithms for indexing, and Chroma do some finally hands-on on the Chroma DB. So I hope like you like this session, and if you have any questions and comments, please ask it below. I will wait for it. Thanks for joining the today's session. Thank you very much.